Great. My name is Anca Dragan. I run a lab here called the Interactive Autonomy and Collaborative Technologies Lab. And we also work on augmentation. Not so much augmentation with virtual characters like you have in virtual reality, but augmentation with real characters, namely robots. So what we care about is how we might bring robots into the world in a way that actually helps and supports real people. And if you think of robots today, so what do I mean by robots? I mean things like autonomous cars or arms that can help people with motor impairments, or robots in your home, like personal robots that might help you prepare a meal or change a bed sheet or something like that. Those are the kinds of robots that I'm talking about. And if you think of what they do today, well, here's how we program these robots. Let's take the example of an autonomous car. We have an autonomous car, and we come up with an objective that says, here's the destination. You need to reach the destination. And then we also augment that objective with sort of constraints, things that the robot shouldn't do. Like, for instance, you have to stay on the road, and you can't hit stuff, right? Now, here's the interesting part, which is where my interest lies. If there's a human around, like a human-driven vehicle in this case, then that human to this car is an obstacle that needs to be avoided, right? Which makes sense. You don't want to hit other cars on the road. So far, so good. But if you think about how we work, and by the way, we'll have some examples beyond autonomous driving as well, but let's stick to autonomous driving for now. If you think about how we drive, so I got a car recently because I moved to San Francisco and I have to commute, and it's on the Bay Bridge every single day, and there's a lot of traffic. And so here's what happens. Every single day, some person starts merging in front of me, and what do? Well, I have to brake, otherwise I would actually collide with them. And so if this were an autonomous car, and it would assume that I'm just this obstacle that is going to keep doing whatever it's doing regardless of what the autonomous car does, then you would never see situations like this, right? Because this car would say, well, this person is going. I don't have time to go in front of them, so I'll just wait, right? But if you just wait, then your autonomous car will be stuck there forever and ever until traffic clears off. So we don't want that. At an intersection, also we don't treat each other as obstacles, right? We might start inching forward to sort of assert that we're going first. And then the other car might hit the brakes to let us do that, or might accelerate to make sure that they go first. Regardless, right, we don't treat each other as obstacles. We actually have some sort of coordination going on. So this was the autonomous driving domain, which we work with a little bit. But my background is really in the manipulation domain. So manipulation means how you can use robots' arms and hands to physically change the environment and achieve useful tasks. And there as well, the paradigm is, I need to reach a goal. Like, if I need to grab a cup, I need to get myself in a configuration that enables me to grab that cup. And I need to avoid collisions, right? If I do it, I can't. If I reach for that bottle over there, I have to make sure I don't hit this. I have to make sure I don't hit any people. And again, people are obstacles in this paradigm. Here's kind of a fun video. This is a robot. And it's going to play for you 20 different trajectories that it can take to solve the problem that I just mentioned. So it starts in a particular configuration, and then it reaches one configuration that enables it to actually grab the cup, and doesn't hit stuff, right? But the way you do that, there are many, many, many different ways. And from a functional perspective, they're all just as good because they all achieve the objectives that we gave the robot. And again, if you think about how we work when we manipulate, especially if you want these robots to actually be doing manipulation because it's useful to people, well, when I cook with my fiance, I don't treat him as an obstacle. I try to look at what he's doing. Sometimes he needs a bit of help, honestly. But I try to look at what he's doing. And maybe as he's finishing chopping the vegetables, I get the bowl, right? So again, we see coordination. He's not just an obstacle, and I do my job sort of and try to avoid him and not collide with him. I actually interact with him, right? And it turns out that if you do treat people as obstacles in manipulation as well, so with cars we've seen that maybe you get in trouble because you're not as effective. With manipulation, this is my favorite video. Please don't take pictures of this video because it's from a user study. But I love showing this because it really shows what can go wrong. So here we have a robot that's using this kind of motion planner that's trying to reach for a cup and avoid collisions. That's what the robot is doing. And it's going to reach for one of these cups. And here we have a person who actually needs to coordinate with this robot. In particularly here, the coordination task is they have to decide on a common color. She's gathering the ingredients for her side, and they have to bring everything over here. And then the task repeats. So the robot starts moving. And again, the robot is avoiding collisions and achieving its final destination. But she's pretty surprised. And then she look at her right hand. She hesitates a few times, and then only finally she realizes, oh, OK, we're doing orange, so I can grab the orange ingredients and move everything over. Here it is in slower motion, and you can really see this like internal tension that she's feeling. She's like, no, yes, no, and then she starts. So this is what happens. Coordination breaks down if all we care about is obstacle avoidance. And you might think that maybe, well, the robot moved in a weird way. If we just made it efficient and sort of it took a more natural motion, everything would be fine. But here's a little game that we can play. So this robot is going to move to grab one of these two bottles. Which bottle is it reaching for? Pretty hard to tell. It's usually about 50-50 when I ask people, and it's actually this one. So again, it's not just about obstacle avoidance, and it turns out it can't just even be about efficiency. There's actual coordination mechanisms that we need to work on. So sort of the bottom line, and the idea that we're using in my lab is to say that we're not just obstacles that robots need to avoid us. If robots are really going to be useful and out into the world, and the world has real people, they'll need to actually coordinate with us. And that raises the bar for the kind of autonomous behavior we'll see. So a few examples of the sort of things that we're thinking about. One of them is how you can make sure that the robot's intentions are very transparent to people, right? So if you know what the robot is going to do, it's easier to coordinate with it. So here's an example where the robot's objective is no longer just to reach that bottle and avoid collisions. It's also to maximize the probability that you, as a human observer, will figure out that it's grabbing the bottle on the right and not the one on the left, right? So the robot, in this case, actually figures out that it can exaggerate the motion to the right, and that makes it more clear that it's grabbing the object on the right. And this is really cool because you see animation using exaggeration all the time. But what's interesting here is that we were just able to set up a nice objective that now actually reasons about people, and the robot figured this out. We didn't have to hand code it in any way. Here's another example. So beyond the immediate goal of the robot, usually in a task you have this sequence of steps that you need to achieve, right? It's not just I move and then the world ends. It's I move and then I do something with the object that I picked up and so on. So in that kind of situation, it's important that people actually figure out what the sequence of steps might be so that they know what they should be doing as well. And we're looking at and we're abstracting away this task with a little robot that needs to hit all of these different targets. But the way it hits these different targets, it's sort of up to it. You don't actually know. And if this is the first step in the task, if you see the robot going here, then, well, what do you think it's going to do? Probably go here, right? And then what? Maybe there, or maybe there, and then around, right? So there's one option that's this option, which is pretty good. There's this option, which is also pretty good. And if you're a human observing this, you might not know which option the robot is going to pick. They're actually both pretty efficient. And so when a robot like this that's optimizing for efficiency only actually starts coordinating with people, suffice it to say, people get pretty frustrated. I anyway. And so what our robot does, again, what we tell the robot is don't just find a plan that's efficient. Find a plan such that when the person observes the first parts of it, they'll know with high probability what the rest of it is going to be. And so the robot decides to go here first instead. It's not as efficient, but after it goes here, it's very clear what the continuation is going to be. And then in the autonomous car land, this was all about the robot expressing its intentions so that people can better coordinate with it. We're also looking at the fact that it's not just your mental state that changes, your beliefs about what the robot is doing. It's also the actions that you take that are changing. And so we started looking at how we might learn those sort of responses. And one thing that came out of this is I have time to show you one example, which is my favorite example, at a four-way stop. So I don't know about you, but I always have trouble at four-way stops because I end up coming to it at the same time as another driver, and then I wave, or I flash my lights, or, and then if you have an autonomous car, it's hard for it to do those sort of things. So how does it coordinate? Well, right now, you have engineers that sit down and sort of hack in behaviors, like I'm going to make my car inch forward, or something like that, right? What we did is we learned a model of how people respond to robot actions, and then we used that model to say to this car, look, try to get the person to go first. So a very polite car, but that wants to resolve this sort of coordination behavior in one way or another. And so instead of just sitting there and hoping that the person will proceed, what the car does is it actually decides to start backing up. I was really surprised by this at first, but I really love this example. It's not something that you might think of. It turns out we did human subject studies on this, and it works really. It's very effective because essentially what's happening is if I start backing up, my velocity is going this way, right? So there's very little chance that you as a human will be afraid that I'm going to run into you, right? So you're more incentivized to proceed. So that was kind of neat. And then finally, talking about augmentation, one thing that we've been thinking recently is if we react to robot actions like we do here in driving, right? Well, like we do when a car starts merging in front of us. We also react to robot actions in manipulation. And is there any way that we can leverage robot actions to make us better at the task? So here's what I mean by that. We look at one specific example with it, which is handovers. So imagine you have a robot that's handing you over something, and then you have to take that object and do something with it, right? So it's sort of part of a task. And one interesting thing that we've observed here, sort of to Bjorn's point about problem solving with people, this is a very low-level kind of problem, but it turns out that when the robot hands you over an object, you're going to take it in the way that's most comfortable to you. But that way might get you in trouble when you're trying to actually use that object. So if you have a particular goal, like you have to stick it in the dishwasher or something like that, you might have to re-grasp it or bend your arm in some way, right? Because it turns out that we're not very good at thinking a few steps ahead. We're tempted to just do it in the way that's more reasonable then, but not very good at saying, but I should take it this way because I'm going to have to put it in the dishwasher. Sometimes we do that, sometimes we don't. And so what we realized is, well, the way the robot hands you the object actually influences the way the options you have for taking it, right? And so if we gave the robot the objective function of maximize the person's comfort at the handover time and at the goal, the robot starts giving you the object in such a way that whatever the most comfortable, the myopic way you're going to take it, that way also works for the goal. So it's the sort of thing where the robot decides to give you the object in a more awkward way for itself, but who cares? It's a robot. It's not like it. But then what that means is that even if you don't plan ahead, the most likely solutions you'll come up with are also going to work when you're actually going ahead and doing your goal. So it's a way of sort of, I think it relates to what Bjorn talked about, right, of augmenting people to get them to be better at the task. We're not projecting anything, but we're using the robot's physical actions to sort of guide you and nudge you to be a little bit better at your task. Good. So overall, this goes back to we're not just obstacles. robots need to coordinate with us and understand that we're agents that take actions, that respond to their actions. And in all of these examples, really the underlying technical approach was to say, I have a robot, but its actions are not just affecting the physical state. They're also affecting what people will believe and what people will do. And we have to take that into account. And that's what the Interact Lab is about. Thank you.